and welcome to this month's Self-Build Hour. I'm Jenny Chandela. I am the host of the Self-Build Hour and architect and associate with AC Architects. I am here filming from the National Self-Build and Renovation Centre in Swindon. Back to typical, they've finished a lot of the construction that was going on here, so it's a little bit quieter, so I can be in my normal space. So for those of you who are perhaps joining us for the first time, just quick check on logistics. So we will be filming this Self-Build Hour, and that allows those who want to go back and revisit the information or weren't able to join us live are able to see it later on. So we have a whole catalog of all our previous Self-Build Hours. If you haven't checked them out, please do that. But for the benefit of those who are here today live attending, you have a Q&A function. In that function, go ahead and type in any questions that you have for today's presenter along the way. If you don't have the Q&A function, that's absolutely fine. Just go ahead and use the chat function, and I'll also be checking that. So without further ado, I will go ahead and get started in introducing David. So we're really happy to be joined today by David Hilton. He's the Director of Heat and Energy, and he's a recognized expert in sustainable building, energy efficiency, really, and healthy homes more broadly. Those of you who are familiar with the NSBRC and HBR are really probably already know David already. He's a trusted advisor for both of them, and he's passionate about helping self-builders just like you sort of cut through all that noise, focus on delivering something that's practical, cost-effective, and will future-proof your energy solutions. So please join me in welcoming David to this month's Self-Build Hour.
Thank you, Jenny.
You're very welcome.
I'm pretty clued up on the housing bit. It's just this Teams bit that is going to be the difficulty. So would you like me to share now?
Yeah, go ahead and share your screen. Sure. And I'll turn myself off once I know you're in good hands. I can hear you and I can see you, so that's a good first start.
Absolutely.
I can see that then. So I'm seeing the whole PowerPoint.
Are you seeing the whole thing now?
Yeah.
I hope. We can just carry on. I can't
Perfect.
see you anymore, but we did practice this, so we know that that's normal.
Yeah.
I will carry on from here then.
Okay, brilliant.
Perfect. Thank you.
Thank you.
What I'll do is I'll start talking to you about heating solutions for your low energy home. And a lot of these have been drawn and changed slightly from the home building and renovating shows. So apologies to those that have seen some of it before, but I have a strategy really, and I call it my 3D strategy, where I look at 3 distinct Ds that will help you create the journey to your low energy home. And the first D is just define. And the define is the concepts, it's the ideas, it's really your brief and everything that goes into it. Once you've got the define bit right, that's when you go to the second D, which is design. And that's when you start putting numbers on it. How big is it? Where does it go? And you start detailing it, and when you'd actually need to start putting it into your actual build schedule, and also how much it costs. And that might then send you back to define again to be able to really work out if it needs to go in or not. Once you've got the designs absolutely right, and you need to get these right in the beginning, don't think about, right, we'll start building and we'll get up to wall height and then we'll work out how all of this stuff goes in. That's not the time to be doing it. You really want to get the designs absolutely right. Take off your design hat and start putting on your building hat, because the third D is the delivery. And the most expensive thing you'll change in your build is your mind. So try not to do it while you're building. What you really want to be doing is changing your mind at the define stage, because then it becomes easy. If you do have to change your mind at the delivery stage, I do hear it a lot. I'll be on site. Homeowners will come to me and say, we've been thinking, now's not the time to be thinking. But if you have been thinking and you've seen something you want to change, you've got to go back to the define stage and make sure that everything else is still compatible and everything else still makes sense. So when I look at this, I always say aim for zero, and zero is quite a broad spectrum term. It could be zero carbon, could be zero cost, could be zero bills. There's a number of these concepts going around, but if you aim for zero, doesn't mean you're always going to get there, but if we aim for it, let's sort of see how low we can go as far as that goes, so that we can actually get in the stuff that makes sense to us and just say, and let's do this at the define stage. Let's aim for that zero. And if we're going for 80% reduction, then that is what we're doing, and we will then be able to design something that we can actually build. So when it comes to eco, there's two ecos in every property that you build, and the first one is your sort of eco logic. That's where you start thinking about natural products and low energy and all of these things. But then the other eco is the economic, and the two have to balance out. And you really don't want to be sort of massively the most expensive home in the street. I think mine probably is, but you know, from that point, you'll never get back what we put in, but we didn't put it in for that reason. And I think that being a guinea pig is also not a good thing. You want to make sure that whoever's putting stuff in, you're not paying for them to learn their trade. You really want to be using people that are seasoned professionals. So really balance up the ecologic and the economic together. Now, when we start looking at the define, in order to be able to get those concepts, I usually have 3 columns. And the first column is what was also 3Ds, strangely enough. The first one is what you will definitely have in your home. It's a must-have. In my property, or if I moved, a definite thing that I would want is a built-in barbecue area. It's not negotiable, it's happening. And it's a lifestyle choice. You're building a home, you're not just building a house. So it's not I must have walls and I must have windows and all of these sorts of things. It is more about the things that make your home a home and the things that you must have for that. The second column, which is the desire. What would you like to have if the budget allows? And there might be a very, very thin line between definite and the desire, because you might think, I want a built-in barbecue, but if I can't quite afford it, I will create an area ready for it. And when I have a strategy, I can put it in later. Very often fancy kitchens and things like that get put in as a desire with a strategy to change, and then allow it to change. Tile the whole of the floor so that when you change from a breakfast bar to an island unit, you don't have to then find a few more tiles and redo the floor. At least you've prepared for change. Things that might change as well is, especially if you're building in England at the moment, you can still build with a new build with a gas boiler if you've already got permission in place, planning permission. And you might then say, I'll still put the gas boiler in, but let's equip the whole home to take a heat pump so that when we do a transition, that it becomes a very, very easy change to make, and everything's been prepared for it already. Now, the third column is as important as the definite, and it's the don't. It's, for whatever reason, a professional in the industry might think that it's a no-brainer that of course you're going to want to have solar panels on your roof or a heat pump, but you might have a very, very good reason why you don't want them. You might feel that solar panels blight the architecture, or you've got nowhere for them, and you simply cannot put them onto your building because you don't like them. And that could be any detail of your building. And I would personally, as a design engineer, I want to know what you don't want as well as what you do want. And then we can make sure that we exclude them. And you don't have to have a reason. You just say, I don't want that product. Now, in England, currently 80% of our properties are heated by gas boilers. And that equates to around 1.7 million boilers being changed every single year and sold in this country. Now, in Scotland, you cannot put them in. The new build heat standard banned them from 2024. So anyone building a new build in Scotland, you will not be putting a gas boiler into it. And we do see on existing buildings, if you're doing a major renovation, that you can still keep your gas boiler, but it might be worth thinking about the strategy for change to move away from gas. The costs of gas are going to go up, and what they call the spark gap, which is the difference between electric cost and gas costs, is closing. It used to be around 4-to-1. You would get 4 units of gas for the same price as 1 unit of electricity, but that gap is now closing. We're seeing more tax slowly being loaded onto the gas and taken away from electricity, just to even it out a little bit. So that spark gap is changing and swinging the pendulum firmly in favor of electrification. And a new sort of catchword that's being bandied around is what they call electrotech, where all of the technologies that you use in your home are going to be electrically based. And if you're going for an electrotech type of property, do make sure that all of the products can speak in a way to the controller, because not all of the heat pumps and vehicle chargers and things like that actually have similar softwares. So you need to be able to make sure that they can all speak to each other and are compatible if they need to speak to each other. It is true to say that each of these individual units will work by themselves, but if you want them to be able to work at specific times and coordinate with other things, then you do need to make sure that the softwares can converse across all the different technologies. In England, as I mentioned, the Future Home Standard is now here. From March this year, March, April, basically it's been introduced. From 2027, you will then have 1 year from March 2027 to be able to finish your home, and you will then, after March 2028, you will not be allowed to put a gas boiler in your new build home in England. Future Home Standard does not cover Scotland. Now, right now, you could put a gas boiler in, and if your plans are passed before March 2027, you will still have that year to be able to complete your build and be able to get the gas boiler into it. After that, no more gas connections. On existing buildings, there was a date to ban gas boilers being replaced in existing buildings by 2035. That date has now been scrapped, and no new date has actually been put in place. So we don't know what's happening as far as that goes. A lot of guys are also saying that as far as politics go, if Uncle Nigel happens to get voted in, what will happen to the Future Home Standard? Honestly, I don't know. So please don't put that in the chat and say what will happen if Uncle Nigel comes in, because nobody knows apart from him. Now, what's the low-hanging fruit? Well, photovoltaic panels have been around for a long time. They are the solar panels that generate electricity from the light of the sun. So shading is very, very detrimental to that. And you will get, on a good day, you will get very, very good generation, but as the light dims on a cloudy day, you will get less. And as you go further north, your yield is less as well. Now, you do need quite a few panels. That's quite an old system on the top left of the picture. So you don't really need to have more than around 10 panels now. You can have more. If you're on a 3-phase electric supply, you can have 3 times as many without planning permission or permission from the network operator. But if you go above sort of 4 kilowatts worth of panels, which is around 10, then you do often need to get permission from the grid to connect more back, and sometimes they will limit how many you can put on your roof, and especially how much energy can go back to the grid. As we move to the right, we then have solar thermal panels, and they are also solar panels, but they generate heat from the heat of the sun, and that heat is usually used to make domestic hot water. These panels have not been that popular while we've seen the massive uptake of photovoltaic panels, simply because most people would have got their solar photovoltaic panels on their roof. They would have redirected the energy to the heating element in their hot water tank. So when they have excess generation during the day, it would simply dump the energy onto the hot water tank. So you didn't really need the solar thermal panels. But now, with the sort of popularity of batteries and more electric vehicles being connected to our homes, we are seeing solar thermal panels coming back, simply because we're using the electricity more appropriately elsewhere other than just topping up a hot water cylinder. So solar thermal panels are coming back, and in fact last year we saw the introduction of a new apprenticeship which is all about low carbon energy systems, and that apprenticeship focuses on heat pumps, ground source and air source heat pumps, as well as solar thermal systems. So definitely a product that is in the radar, albeit I would think on a new build that you would aim to let the solar thermal cover part of your hot water creation rather than try to make it do your central heating. There's just not enough energy from the sun during the time when you need heating. That becomes the issue. As we then move clockwise round again, we come to biomass, and biomass is still a valid alternative to fossil fuels, but I would use it appropriately. If you've got a resource of biomass, whether you've got logs or wood chip availability, then it definitely becomes a resource for yourself. Log burners, I know a lot of guys are banning log burners, saying ban them. Personally, if we ban log burners, it's a slippery slope to banning barbecues, and I don't really want to go down that road just yet. If you're going to have a log burner, try and get one with what's called a direct air intake. The direct air intake simply means that it gets its air that it uses for combustion from outside of the building. So when you've got your airtight home, then you're not depleting the oxygen levels inside the home and affecting the air quality. The heating appliance simply gets its air for combustion from outside, and it puts the proceeds of combustion, the waste, out through the flue or the chimney as such. So by all means, if you're going to go down that road, try and specify which log burner you're going to have before you start designing up the fabric of the building, because you will need to have further penetrations through the building to be able to get the air in and out of the flue. So knowing where those are, if you can download the installation manual, that sort of thing, prior to getting all your structural drawings complete, then at least it can be planned in. Then we move across to heat pumps, and a heat pump does not actually burn any fossil fuels. It doesn't have combustion, and all of those boilers and biomass and all of those things that burn fuel, they make a lot of heat in a very, very short space of time. But a heat pump, because by the nature of how it works, which is to move heat from one place to another, it simply moves heat from the air, from the ground to your home. And because of the way that it works, it actually moves a small amount of heat over a long period of time. So you need a fairly insulated and controllable home for heat pumps to work efficiently in. And everyone watching this, whether you're watching it live or on catch up, will have at least one heat pump in your home. You call it a fridge. and it's moving heat from one place to another. So it's moving heat from the products in the fridge to the grid at the back of the fridge. And in the same way that if you had a very, very hot day and you thought, I will open the fridge, that will cool the house down. Well, it won't cool it down very much. And I think we would all agree that it's not the right appliance, because basically the engine isn't big enough to cool the volumes that we're trying to cool. So with a heat pump, it is imperative to make sure that we know how much heat we've got from the resource, whether it be the air with an air source heat pump or the ground with a ground source heat pump. And we also have a heat loss calculation to know how much heat we need in the home. So we know how much heat we've got from outside, and we know how much heat we need in the home. That way we can then quite accurately size the engine that's going to move the heat from one place to the other. And yes, there's a bit of science that goes into it, but it's not something that's brand new. And if we get that equilibrium right, we get the efficiency right as well. Now, that brings us on to design. And within design, you guessed it, we've got 3 Ds. What we need to know is the dimensions. How big is this bit of kit? How many ducts has it got going onto it? Where do they go? How much space do they need? Do we have to have holes drilled through structural elements of the building? The second D would be the dates. When does it have to go in? Clearly, we don't want to have to start putting ducting in the roof once the ceiling's already gone up. We don't want to be putting we certainly don't want to put in products when there's going to be lots of mess and plastering and stuff messing them up. So getting the dates right, getting the project management, the Gantt chart organized of what happens and when does it happen and how many people will be doing it is very, very, very important. And the third D, poetic license on this one, dosh, how much will it all cost? Because at the design stage, we just want to know, can I afford it? When will it go in? How big is it? And that is kind of that makes it finite. After that, we start looking at different things. And when it comes to air source heat pumps, just to give you an indication of dimensions and things like that, the cylinder goes inside the home. You need a hot water cylinder. It's not like a combination boiler where you have instant heat. It doesn't work like that with a heat pump. You do have to have a hot water cylinder built into the home. And the hot water cylinder must be a heat pump compatible hot water cylinder. Different heat pumps have different requirements, so it's usually best once you've specified which heat pump you want to make sure that the cylinder is compatible with that heat pump. The air source heat pump goes outside the house, and you need a fair amount of air and space around it. What you don't want to be doing is parking your Tesla straight in front of it, because the air coming out of it is a lot cooler. More on that a little bit later. And that air must never ever get reflected back so that it goes back into the heat pump again, because you will just get short cycling. So that air that comes out of the heat pump must dissipate. And ambient temperatures outside, it doesn't really matter how cold it gets, down to sort of -10, -20, sometimes different manufacturers, it will still operate, because inside an air source heat pump, the refrigerant changes from a liquid to a gas. It boils at about -45, -50, depending on which heat pump you've got. So -50 thinks that -10 is still positively tropical. All heat pumps do need planning permission, but most of the time they will fall under what's called permitted development, so long as you meet certain criteria that it's not going to adversely affect or impact the neighbors from a sound perspective. And how much noise do these things actually make? Well, ours, I guess it's more of the hum that is what you could potentially hear. And it's a bit like putting a microwave oven outside. that would be more of the sound. It's the one thing we don't hear, simply because when you want to run the heat pump, usually the doors and windows are closed because of the central heating. They are very much suited to being in underfloor heating, but can also go into radiators. We simply design them to be compatible. With the air source heat pump, we can see that they are distinctly beautiful things to look at. So you really need to put it right at the front of your house, hide your Bentley and your Tesla and everything behind the back of the home. We want to see this beautiful heat pump. And when we look at it with thermal imaging, we can actually see cold air coming through the heat pump. That air could be 12 degrees cooler than the air going in. So even if it's 7 degrees outside, that air coming out of the heat pump could be -5, and that will start freezing things, pot plants, delicate foliage, could freeze your pathway when you're not expecting it. And you certainly, as I mentioned before, don't want to be pointing it at your Tesla. You don't want to be freezing that up as well. So the heat then gets moved across, it gets carried across to the radiators, which are no longer radiating. They are now at a low temperature. They are convecting. And those radiators are approximately 38 to 40 degrees, about the same temperature as your shower, that when you're actually showering in it, not the water as hot as it can get, but around shower temperature. And they're on for a long time. And the design methodology for a heat pump is that you don't turn it off, it runs when it needs to. Just the same as you don't actually turn your fridge off, it only runs when it needs to. So you keep it on, you target your temperatures in the room, and the heat pump runs when it needs to, in order to maintain the temperature in those rooms. Now, because it's low and slow, the heat pump really wants to have a lot of flow of water going in. There's only 2 ways to get more energy into a home in water, and that is either make it hotter or move it faster. And the issue we have is that you then need bigger radiators. So, and a lot of guys get concerned about this and think, wow, I'm going to have to make all my radiators 3 times bigger. Now, when we changed the heat pump in our home, we changed 2 radiators only, because all of them were already oversized. And if you're designing a low energy home, your radiators in your underfloor heating will already be very, very low temperature. They will be a lot smaller, especially the radiators will be. They'll be a lot smaller than ones you expect in an existing home, because the energy is so low on them. So don't be worried about having acres of radiators. That's not what one gets. Now, when we have low temperature, we do need a faster flow. One of the anomalies here is that if you run, we get slightly technical here, if you run water through a pipe faster than 1 meter per second, you start hearing it. Once you get to just over 2 meters per second, you are at the same noise as your heat pump would be outside. So you've got to about 40 decibels at that point. And that is the maximum. So you really want to keep your water at 1 meter per second in the pipe. So if I want to move twice the volume to get twice the heat in, I need a pipe that carries twice the volume. So I put bigger pipes in. So most of the time, if you've got micro bore in an existing home, that might need to be changed depending on how it's designed. And very often with a heat pump outside, we would expect to see 28 millimeter pipe at least going from the heat pump to the home, and then distribution in a minimum of 22 mil, and then into maybe even 28 going to underfloor heating manifolds. We want that size. So planning is essential. And this is where I talked about, if you're putting in a boiler, we can still run a boiler on the bigger pipes. What we can't do is run the heat pump on smaller pipes. So if you are putting in a boiler and you haven't done your distribution pipe work yet, design it to be compatible with a heat pump. So design it for bigger flows. The faster flow has that noise risk, and therefore we do need the bigger pipes. One of the Anomalies with a heat pump compared with a boiler is that the colder it is outside, the hotter the radiators get, and they will get up to a maximum of around that sort of 40 to 45 degrees. But when it's sort of 12 degrees outside, 12 to 15 degrees outside, you might find that your radiators drop down to sort of 30 odd degrees, and you start thinking this is not right, because they modulate all the time. What the heat pump's trying to do is match the requirement in the home. So you do get this modulation, and it does take a while to get used to that behavior if one's used to having radiant and very, very hot radiators. So that, I think, is probably the biggest thing that we had to get used to when putting in a heat pump, was getting used to the modulation, that it's all low and slow, and the slower it is, the lower it is. But the colder it is outside, it might get a bit warmer as well. So it's just really a business of making sure you understand that this is how the heat pump works, and it is actually correct. With a ground source heat pump, give or take, very, very broad spectrum, you would need, for a horizontal ground loop, you're collecting heat from the ground. So if you had sort of damp, cohesive soil, you would probably need 2.5 to 3 times the floor area, not the footprint, but the floor area of your home. You would need that as available space outside the home, not under the home. Don't put pipes into foundations and things, because as ice builds up, the ground can move. But you would need to have, so if you had a 200 square meter home, you're going to have sort of between 400 and 600 square meters of ground loop outside. For a borehole, rules of thumb don't really work. You need to get a geologist involved and start getting costs in quite early on. A borehole can be more efficient, but if you get it wrong, then it can cost you an absolute fortune to replace and to put extra borehole holes down and relink the system up. So with ground source, do make sure that you're absolutely confident of your numbers first. When it comes to the ground loops, horizontal ground loops, yes, if you are competent with a digger, you can actually dig your own trenches. The designers will simply tell you how big the trenches need to be, how long, and how many trenches you need. So you could dig them and save money on that as well. Now, how much is enough? When it comes to pushing water through pipe work, there is a calculation for it, but there's not enough time to go through it right now. So what I've done, this is the formula, but I've turned it into, I've done the maths for you. So because of the way we set up boilers and we set up radiators for heat pumps, basically with a boiler, very, very simply, the water loses 20 degrees across the radiator. So the water will go in at about maybe 70 degrees and it'll come out 50 as a scenario. So it's losing 20 degrees across the radiator. That's known as the delta T, the temperature difference. With a heat pump, it's 5 degrees. So you need 4 times more water to go through it. And that affects that formula that we saw. So basically, when you see the pipe sizes on the right-hand side, the purple figure, 5 kilowatts, is if you had a boiler, you would be able to get 5 kilowatts of heat through a 10 millimeter pipe. With a heat pump, you'd only get 1.2. And that's how the formula works. So if we had an existing home and we put a boiler in, we would only need, for an 11 kilowatt load, which is what this one is, we would only need 15 millimeter pipe. And then most of the house would have microbore 10 mil in it. Now, this is not a plumbing schematic. This is simply a mathematics plumbing diagram. So don't think that it's a plumbing schematic at all. Now, you'd come along with your existing home and you'd say, I want a heat pump on it, please. At that point, your 15 millimeter pipe now, because you've got 11 kilowatts going through it, we would go down the graph, 11 kilowatts, we would need a 28 millimeter pipe. The second part also needs a 28 millimeter pipe. the third stage 22, and it's only when we get to the last stage that we can use the microbore pipe. Personally, that home would be a complete repipe. So that is where suddenly hidden costs come in. Now, you might think, I don't want the whole house repiped. The specifier comes along and says, well, you don't need to repipe the whole house, and they trick it by working the formula and leaving the radiators as if you had a boiler. So the heat pump now is no longer trying to heat the water 5 degrees every cycle, which is going to be easy for it to do. It's trying to heat it by 10 or 20 degrees every cycle, so it's working really, really hard. That's a bit like you wondering why you do not get good fuel efficiency in your vehicle, and you're traveling uphill in third gear, high revs into a headwind. You just will not get the miles per gallon that you're expecting. So good design and enabling this thing to actually work the way it was designed is crucially important, but there are ways of actually fudging it so that you can still get the result, but it's going to cost you an absolute fortune to run. So one has to be a little bit careful and a little bit also a little bit aware of what guys are telling you online and saying, oh, just turn your temperature down a little bit, or tweak a few things. Just make sure you absolutely understand what you're doing, and you don't end up with a surprise next time your energy bill comes in, your electric bill. Now, what size heat pump would you need if you're building to sort of passive house levels? Then we would look right across to the right hand side. You're looking at sort of 20 watts per square meter, right down to 10 watts per square meter. And if you were building a 200 square meter home, then, you know, at 10 watts per square meter, you only need a 2 kilowatt heat pump. If you were building to current building regs, you would probably need, therefore, somewhere around an 8 kilowatt, because current building regs has come down slightly since this slide was made. It's no longer 50 watts. It's sort of between 30 to 40 watts per square meter, depending on the shape of the building. So 200 watts, 200 square meters, you would need around 8 kilowatts. Now, if you were specifying an air source heat pump, simply looking at the number and saying, there's a 9 kilowatt heat pump there, what you have to do is look at the manufacturer's instructions and say a 9 kilowatt heat pump when it's really, really cold actually only gives me 6, because it's using some of that energy to defrost itself and losing some of the energy due to inefficiency. It does get complicated, not going into it right now, but look at the manufacturer's instructions to say at cold temperatures, what is the output of that heat pump? Now, for an 8 kilowatt load, I'd be putting a 12 or 14 kilowatt heat pump onto it to make sure I've got enough energy to cover the whole load with the refrigeration circuit, not a backup electrical heater. Now, manufacturers have details too, just the same as they do with vehicles. When I bought my truck, they told me I would get 42 miles to the gallon. Now, not even down a highly greased mine shaft with a tailwind would I ever get 42 miles to the gallon. In real terms, I get about 30, but then it is a truck. And what we have with heat pumps is exactly the same thing. They have this thing called the COP, which is the coefficient of performance, which really means for every 1 unit of electricity that it uses, how many units of heat will I get? And the manufacturers have said they will get 4.35. So I use 1 and I'm getting 4.35 units of heat. Now that's your 42 miles per gallon, because nobody's heating water to 35 degrees in their central heating circuit, not when it's 7 degrees outside anyway, because that doesn't make sense. So when we start looking at real heating at -3, the actual COP on this is now 2.9. So you're using 1 unit of electricity and you're getting 2.9 units of heat. So you're losing something in translation, because those are the real world conditions, and it fluctuates all the time. And you will only get that if the temperature difference is 5 degrees. If you had the temperature difference at 10, you'd be dropping down from 2.9. And sometimes if it's working really hard making hot water, you might only get 1.8, maybe 2. So for every 1 unit of electricity you're using, you're getting 2 units of heat. And this is where the cost of electricity and the time of day when you use it and all of those different algorithms have to come into it to help you manage the efficiency of these systems and use them when energy is cheapest. Maybe when you're generating some from your photovoltaic panels, or if you've got an off-peak tariff because you've got an electric vehicle. Now, when it comes to radiators, we do have to oversize them as well. As I mentioned, sometimes we oversize radiators. There is a formula for it. If you have a temperature difference on radiators from the room to the temperature in the radiator, the room might be 20, the radiator is 70. Therefore, you would then get 1 kilowatt if we look on the correction. So 50-degree temperature difference, it's 20 in the room, 70 in the radiator, we get a kilowatt. That is how radiators are sized. So if you go and buy 1 kilowatt radiator, it's sized at a 50-degree temperature difference. But we don't have 50-degree temperature difference. We're running at 40 degrees. So we only have a 20-degree temperature difference. It's 20 degrees in the room, 40 degrees in the radiator. So we've only got a 20-degree temperature difference. So we only get 304 watts for every kilowatt of radiator we put on. And this is how we size it. We simply use that formula, and all the different variations are there. This is just an overview of it, that the radiators have to be sized for the flow temperature. Otherwise, you will not get the heat into the room. It's as simple as that. When it comes to existing homes as well, single pipe systems in existing homes are not compatible with heat pumps. These were put in quite a while back. They work well if you've got very, very, very high temperatures, but they're not compatible with radiators, with heat pumps. You need what's called a flow and return system, or run it off a manifold. When you have a flow and return, ideally you want the hot side to go in, the flow to go in the side with the thermostatic radiator valve and come out of the other side, which is the lock shield. Most of the time, the thermostatic radiator valves are bidirectional. And in defense of some of the trades, if you have a problem with your radiator, very often the system will be drained down and they won't be able to know which one is the flow and which one is the return pipe. It's not like electricity where we color code. You will just have 2 copper pipes and you won't know which one has the hot supply and which one is the colder return. So sometimes it's not that easy to actually know which way around it goes on an existing building. Now, there are times where it does matter. If you put column radiators in, then if you get them the wrong way around, you will not get the efficiency. So with that, luckily, it's quite easy to change them. You shut down the thermostatic radiator valve, and you can just unhook the radiator and put it back in again, back to front on a column radiator. So that would be quite easy to do. As I mentioned, it's not always easy to know which one's the flow and which one's return. But with column radiators, a lot of them are set up in a specific way that you will not get maximum output from the radiator if it's been plumbed in the wrong way around. With underfloor heating, crucial to get the design right as well. Couple of things here, really. You want the pipes to be as short as possible. Well, not as short as possible, but similar length. So if you've got one 30-meter piece of pipe and a 120-meter piece of pipe off the same manifold, the 30-meter pipe is going to have far less resistance than the long pipe, and therefore balancing becomes difficult. When we look at the shapes on the left, we can actually see that this number A, I would expect that to have bifold doors across the left-hand side. If we look at the one in C below it, I'd expect 2 glass walls there so that the heat goes out to the glass, which is the thermal weakness, and then comes back into the room. An average room, you would have D, which is what's known as a snail configuration. And in a large room, I would rather have, if you needed, let's say, 240 meters of pipe, I would rather have 3 80-meter pieces of pipe than 2 120s, just to get less resistance and better flow. Infrared can be used in low energy homes as well. Try before you buy. Some people don't like it. I use it as complementary heating, so sometimes use a bit of infrared in the bathroom just as a complementary heat, so you can keep a background heat as well. But infrared can be a very good top up, or some way of taking care of cold spaces. But try before you buy. Not everybody likes the radiant nature of the heat. And when we start looking at solar PV systems, not all of them are full-on panels now. You starting to get building integrated photovoltaics, where you're getting fencing panels, roof tiles, and even what looks like clear glass. And those can be built into atria, into fencing, into a lot of different parts of the building. And that stuff is coming now, where we're starting to see lower efficiency from the solar panel, but at least it's taking the place of part of the building fabric. And a lot of guys say to me, why am I being sold 2 inverters? And an inverter changes the energy that the panel makes and turns it into alternating current that you can use in your wall. So very simply, you have your panels on your roof. 4 kilowatts would be 10 panels. It goes through the inverter into your distribution in the house, and then the house uses that energy. You might then connect a battery to it. And because you've got 4 kilowatt inverter, if you only wanted to discharge 4 kilowatts from the battery, you could use the same inverter. But if you then have a large battery and you want to discharge faster than 4 kilowatts, that is the time when you would need a second inverter. If you want to discharge at the same rate as your panels, you do not need 2 inverters. It's a simple maths really on that. When it comes to delivery, once again, you need to describe to the trades. You need drawings, and you need to demonstrate. If you talk in threes like that, describe. So you're talking to them, you have drawings so that they can look at the drawings, and then you actually demonstrate and show by example. Then you will overcome a lot of barriers. When we start looking at things with your project, there's stuff that is known to you. You know what you want in your building, and there's stuff that's not known to you. That's why you're hiring your trades. That's why you're hiring your professionals. But when it comes to the professionals, there'll be stuff that's known to them that's also known to you in the first block, and there'll be stuff that's not known to those people, but it is known to you. What you want to try and do is avoid the risk. The last block is the risk, because it's stuff that's not known to anyone, and it just comes up and causes problems. So what you want to be doing is asking questions of the trade, saying, I want to understand what it is that I'm making decisions about, and you want to tell them the stuff that's important to you. But make sure when you're telling them that it lands, because you want to make this block as big as possible, lower the risk. The biggest issue we've had language barriers where guys just nod. They think, I'll do what I've always done anyway. This homeowner doesn't know. Or we could have learning issues. There might be dyslexia, dyscalculia. The construction industry draws a lot of people that are very tactile, and sometimes they will not answer you. If you say, does everybody understand, they will all nod, and it's really talking in threes helps stuff land. When it comes to the efficiencies, self-builders can now also join. One of the energy companies has started making a zero bills tariff, where if you put in the right amount of PV, the right heat pump, an electric vehicle charger, and a reasonable battery, you can have 0 bills for 10 years guaranteed. They will just manage it for you. You can opt out. You're not giving it to them, so you can still sell your home. You can opt out. This is the way it's going, and it's about technologies that are manageable. And it's no longer okay to have a house with stuff on it. You now need to build a home that allows you to manage it. And you can either self-manage or get an energy company to manage. It's all coming. The choices are yours. And just when you think you knew what all the questions were, hopefully we've given you a whole lot more questions. Thank you very, very much. Hopefully everybody understood everything. Otherwise, I'll be open to questions.
Thank you very much, David. That was really helpful. On this last slide that David is sharing, he does have his contact details, so please be sure to jot those down if you want to get in touch with him. But yeah, just thank you very much, David. That was really useful, I think, an overview of not only where we are, but where we're going, and sort of some of the comparisons between how we're all used to our homes being heated and run versus what some of the technologies that are out there. And some of them are new, some of them are not really new at this point, but they're new to people who have been living in homes that were built in the past. So so that was a really useful overview. We did have one question that was specific about PV panels. It says, what are your thoughts on comparison between roof-installed solar PV and ground-based solar PV that track the sun? Are there pros and cons? Do you have any recommendations? Are there certain times when one is appropriate and the other is more appropriate?
So roof-mounted ones are the easiest, simply because your electrics are right there. Mm-hmm. It makes it a lot easier, but of course it affects the architecture of the building quite dramatically, and even the in-roof systems don't disappear. They then, a lot of guys say, oh, well, I'm putting slate on the roof, I'll put PV in, that'll save me money. Well, the slate is designed to last a lot longer than the PV panel, and when you come to change it, the technology will have moved on and it might not fit. So it might be a false economy. So personally, if it's a simple building, on roof becomes simpler. You might need planning for one that's not on your building, and running the cable to it from the building becomes a bit of an extra cost. If you can have a tracking one, you can have sort of, depending on how it works, you have two different ways it tracks. It tracks daily, and then it tracks seasonally, where it changes its pitch as such. So you get both two axis tracking. You'll get sort of between 30 to 60% increase in yield, but of course there's the setup costs for it. So if you're going to put one out in the garden or away, make sure that it's robust, that you've got good anchors for it and things like that. So there's advantages of both, and I would get costs for everything first before checking it out. Maybe mounting it on the garage rather than the house would be a compromise, but you've got to make sure that the cost of the infrastructure for the concrete and the cable and the tracking unit actually offsets the increase in yield, rather than just putting extra panels on your roof of your garage. It might be more cost effective. So I do like all the systems. I just think that they have a different appropriateness in each situation.
Yeah, I think that's something that was apparent throughout your talk, is just that there are lots of systems out there. Not every system is for every house. Not every house is for every system. So do your research on those and talk to the people who will help. Engage early. Along that.
Engage early. What a lot of guys do, as I mentioned, was they get to sort of the roof height, they're putting the roof on, and then they contact me and say, yeah, we're thinking about maybe we'll put some ventilation in, and a heat pump and stuff. What do we need to do? Well, nothing. It's a bit late. So it becomes very difficult to suddenly do things. So you've got to think about, before you start building, think about everything that's going in, everything that's on your wish list, and start working with the guys.
Yeah, of course. And I guess people are always conscious of cost, conscious of professional cost. So there's a tendency to wait to bring on additional professionals until you know you have certainty of your project moving forward, and you have certainty of some of the construction costs for the bigger elements. In an ideal world, when would you get involved, David?
At the brief, what you really want is just someone that is independent, that sits there at the brief. And very often, I've done it many times, where you sit in with the architects at the brief stage, the homeowner can ask the questions, then they go off and do their own research. They're on their own. And then if they then want, it just takes another hour, and they can then clarify, and maybe another hour once they've got quotes, just to be able to say, what do these quotes mean? Is there something hidden? Is there something that I've overlooked on this? And so you might be paying for 3 hours of time across the whole build, and that it's not like you're spending commercially. A lot of the consultants charging £2,000, £3,000, £4,000, and you don't need to do that, because a lot of the professionals, all you want to do is know that you're choosing the right professional to put it in. And I reckon 2-3 hours is maximum, depending on how much research you're prepared to do yourself. So
fantastic. I mean, it's similar to when we're having conversations about build systems. A lot of times the idea of a modern construction method is new to a lot of people, and they get the quotes back, and all the quotes sort of offer similar things, but there's nuances to them, and it's understanding what those nuances are and being able to speak to people who can pick that apart, and give you a straight run of what the positives and negatives are for your particular.
It makes a big difference as to what your short term, your medium term, and your long term plans are, because if you want to change something and you already built a product that kind of isn't changeable, then you've lost that option. Yeah,
absolutely. I liked what you said within the design stage of your desire may be something that is achievable in the short term. So make sure that that's accommodated in that initial build and delivery stage. So there's projects that are going to be new build, and it's fairly simple. From that standpoint, to start to think about these low energy technologies, because they're obvious choices when you're starting with that fabric first mentality and the efficiency of the build. But in a house that is a renovation, a deep retrofit, at what point does it make sense to start bringing in these technologies? Does it ever? Or if you have gas, just go with gas and do what you can?
There is an argument for gas. There definitely is still an argument for gas in those situations. I think it depends on what your plan is for the building, whether it's the forever home, how far you're planning to strip it back. I'm guessing if you've engaged an architect, then you're doing quite a major renovation. And at that point, I'd be sort of saying, get it stripped back as much as you possibly can, and then really look at what you've got. In order to, sometimes going and looking at a building and it's covered in wood chip and things like that, we just don't know what multitude of sins has been covered up. So we'd be having a little bit of sort of educated guesses, but ultimately with it's really looking at, and maybe even have an initial talk just to say, this is kind of what my wish list is. Is it a realistic wish list for this kind of building? And how far do I have to go in order to achieve that wish? Maybe before you start, you have that kind of, let's just put a pinch of salt onto it and just see what the reality is.
Yeah, great. Thank you. Yeah, I mean, we've done a few recently, sort of feasibilities where we go out and say, well, ideally we want the full thermal package, but we also want aesthetics, and we want this better use of the space, and go out and get that early costing analysis of it, and then you can start to pull back a little bit to see what is sensible.
Absolutely.
So then on the other end of the spectrum, passive house, in a house, well, or maybe not quite passive house, but really, really highly insulated, maybe passive house standard, just not certification. Someone's wondering, would you ever use a log burner? Is that just paying to open up your windows during the winter.
I think that a log burner is something that becomes almost a personal. It's on that desire list, isn't it? It's the must-have list, actually. I must have it, and I've got to somehow make it work because I want it. But sometimes with passive houses, we've seen homes where the guys modify what they're doing and put a fire pit outside, or controlled fire type of thing outside, so that it becomes like on a patio or something like that, rather than in the house, because of that overheating, because the home is just simply going to overheat and you don't want a little tiny fire embering away, because there's no point, the log burner is about fire. Let's get it going.
Right, exactly.
But with passive houses, the other thing on that is, I thought you were going to say, is a heat pump compatible with a passive house? And I question very often, the moment you need less and less and less energy, you question the viability of the infrastructure, to say, well, this bit of kit costs me X £1,000, but I only need pence of energy. Why should I have rather taken something that had less technology, slightly more expensive to run per kilowatt, but I'm using so few kilowatts, it doesn't matter. So I think feasibility works, and the lower the energy of the home, actually the more difficult it becomes to start choosing what's going to do the heating, because you're going to probably find that you're going to use as much, if not more, energy doing your hot water than you do your space heating. And suddenly you then say, okay, I need a technology that's suited to doing hot water, and then I can also use it to do the space heating, because that's the lion's share. So it's really defining what it is. That's part of that define thing. Define what you want, and then we can find the solutions that work for you, and get them planned in.
Fantastic. Well, I am conscious of time. There's one more question that's come in that is sort of a fun question. So okay. I will end with it. But it says, would you agree that mounting expensive air source heat pumps outside the house is just seeding a massive future crime wave?
I think the batteries are going to be the ones. Air source heat pumps, I'm not sure. The guys will probably nick them for metal weight, but there's a lot of inverters and batteries that are now being mounted outside the home. And I think those are the ones that people are going to come and nick, because those are thousands of pounds. So
they're easy to.
So I guess it goes back to oil and sort of says, yes, you've got to have them available, but you've got to protect it as well on that. So ultimately, somebody wants to come and nick the heat pump. Well, hopefully it's not on the front of the house anyway. There are slight planning constraints on putting it on the front of the house if you've got somewhere else to put them. And if you park your car there, it's going to be blowing cold air at it and things like that. But yeah, I do get it. There's a lot of stuff now with batteries and all sorts of other things where people are going to nick them. In fact, we were reading the other day that somebody nicked a really expensive front door. So really? They came home and the front door was nicked. And you're like, okay. The front door was there to stop stuff being nicked, and that's what they nicked.
Really, anyway. That was the most valuable part of the house.
Yeah, exactly. So, moving on.
Well, we will. It is after 2:00, so I will thank you very much for your time, and remind everyone that David did share his contact details, so please do feel free to get in touch with him with any additional questions that you might have. He'll be happy to help guide you through the next stages of your project. And just as a reminder, there are some in-person opportunities, some of which that David will be at as well. So yes. HBR Surrey is coming up, and that is at Sandown Park, 27th, 28th of June. So in just a couple of weeks, really. We have ACA have a few self-build seminars coming up. There's one in our Scotland office on the 4th of July and one here at the NSBRC in Swindon on the 11th of July. Feel free to get in touch with me if you want more information on those. They're both free and on Saturdays, and are not just architects talking, it's architects and the entire design team talking. So it's a really good overview of a project and what you're getting into with a self-built home. Do join us next month. We will have Rachel O'Donnell joining us to talk about construction admin. That is once again the second Thursday of the month, the 9th of July, and 1 o'clock here on Teams. We look forward to seeing you again. Thank you very much for your time and attention today, and we look forward to seeing you all next month.